Hello everyone. It is my great honor to report here our recent work in PSF, Precision Spray Forming Technology R&D, and its commercial products. PSF is a unique green metallurgical technology for making high-performance metallic materials. Spray forming was invented in Britain in early 1970s. Its solidification cooling rate is around 10,000 degrees Celsius per second, about 100,000 times as high as that in casting. As a result, such solidified metals have fine and uniform microstructure with hardly any macro segregation. Spray-formed metals have normally 50 to 100% higher impact toughness and about 20% higher tensile strength, better cold and hot workability, and better machinability, as can be seen from next two pages. As seen in the microstructure comparison, the carbides in spray-forming steel were equiaxed, about 5 micrometer, due to ultra-high-speed solidification. The same features apply to aluminum, copper, superalloys, and other alloys. This picture compares spray forming with traditional steel making, VIM, ESR, and VAR, and PM, powder metallurgy, of high-performance steels. It was used to be recognized that PM process should make the best high-alloyed steel. Now, our R&D reveals that PSF makes as good steels as PM, but with much short process flow, and much better techno-economic benefits, meanwhile, pollution-free and energy-saving. Such microstructure and property advantages fascinated massive R&D for spray forming of near-net shape PSF for nearly 30 years. However, such efforts interrupted at the end of last century due to a few technical obstacles, such as atomization method, substrate materials, etc. Through an R&D project 2000 to 2003, a Chinese scientist dissolved those obstacles and established precision spray forming (PSF) process. The inventor of PSF technology is Yang Yunfeng, who received metallurgy Ph.D. of Tsinghua University at the end of 1985. During his 50 years career, he worked as engineer in workshop, university professor, chief research scientist in R&D institutes, and managing director in manufacturing companies. He won China Natural Science Foundation's Youth Fund in 1988 and several national awards in R&D, for instance, Award of Innovation Finland 2009, and First Prize for Technology Progress in China Automotive Industry. Recently, he won Best Technical Paper Award at the 75th 2024 World Foundry Congress. PSF technology enriched metallurgy theories and practices. Under his leadership, for last 10 years, Feng He has developed numerous high-end metallic materials, ferrous and non-ferrous, with advanced cost performance. At the early R&D stage of PSF in VTT, Technical Research Center of Finland, near-net shape tools include die casting molds and forging dies, etc. The PSF forging die shown in bottom left corner had spontaneous improvement in lifetime, costs, and lead time. Key persons from the company Osprey, the inventor of spray forming from Britain, came to VTT, Technical Research Center of Finland, studying, bearing only surprise as to how such difficult tech obstacles were overcome. Because of systematic optimization, PSF is more stable in producing special steels, especially high-alloyed steels, such as cold work steel and high-speed steel. Several PSF steel plants were built up in China, capable of making 6-ton steel ingot, which is the biggest in the world. Hot work steel is another tool steel used for tooling of hot forging, extrusion and die casting, etc. Double, even quintuple lifetime was reported from our customers. PSF cold work steel has been used for wear parts by world's leading mining machinery company for more than a decade. Another example is punching die shown in the pictures. PSF D2 has much better microstructure than that of ESR D2. Its impact toughness is doubled, even tripled at the same hardness. HRC 60. Lifetime is about 3 times improved. PSF 1822 is a best-selling cold work steel due to combination of high impact strength and wear resistance. It widely used for mining tools, tunnel boring machine, TBM, cutter, stamping or forming tools, punches and dies, thread rollers, powder compaction tooling, blanking dies, knives and slitters, shear blades, fine blanking tools, scrap choppers, cold heading tooling, rolls, plastic injection feeder screws, etc. Lifetime is improved by 2 to 5 times. As a result of the fine structures, high-speed steel, such as PSF M2, increases impact strength by 100 to 150% at the same hardness. HRC 66. Cutting tool lifetime of PSF M2 increased by 2 or 3 times over ESR M2. Some high-speed steel applications are shown here. The lifetime of PSF M2 broaches increases to 5 times comparing to ESR M2. A PSF-M3 injection rod's lifetime increased by 30% comparing to PM-M3. These pictures make a comparison of PSF high-speed steel with PM high-speed steel. Though difference is barely distinguishable, other structural and performance advantages are still present. Wear-resistant lifetime of PSF steel is increased by 40% higher over PM counterpart. Good industrial application results also received with high corrosion and wear-resistant steel, and with wide applications, including but not limited to outdoor knives, injection rod. Our PSF nitrogen-containing mirror steel is shown here. Its nitrogen is approximately 600 ppm. Surface roughness is polished to about 1.92 nanometers, as shown in the bottom of the report on the right-hand side. As discussed above, PSF steels have much better mechanical properties and tooling lifetime. PSF can also reduce material cost by spay-cladding to make bimetallic material and tools. This figure shows a bimetallic gear hob. Its outer part is made of PSF high-speed steel T15M and inner part is of normal tool steel H13. The microstructure of gear hob shows PSF T15M on the left and H13 on the right, with metallurgical bonding between the two materials. That way, better lifetime is kept and raw material costs are reduced by half. Another PSF advantage is to make hollowed billet, through which some demanding alloys, such as superalloy, can be easier manufactured because of shorter process flow and better material yield, and therefore improved techno-economical benefits. A remarkable PSF progress is high-strength alloys. The microstructure of spray-formed alloy is uniform and fine, obvious better than that of cast. Mechanical properties of PSF 7A61, as an example, are better than 0.45% carbon steel, whereas its specific weight is 1/3 of steel. And its specific strength is higher than most of titanium alloys. High specific strength offers great potential to weight reduction of components in vehicles, electronic devices, robots, etc. High silicon alloy, which cannot be produced by traditional casting with more than 50% silicon, can be effectively made by PSF. You can see that the primary silicon phase is very evenly and finely distributed, comparing to very rough and brittle as cast structure. Examples of high-end applications include chip sealing case and noise-free bearing. PSF is an efficient way to make particle-reinforced metal matrix composites. The photo shows 10% silicon carbide particles of 10 meters uniformly distributed in alloy. It is of the same easiness to make particle-reinforced steel or other alloys. At the same modulus of elasticity, PSF can achieve better tensile strength and yield strength than PM counterpart. PSF is also a cost-effective way to make superalloys. The uniform and fine microstructures result in better hot and cold workabilities, reliable strength, and higher material yield. Super high solidification cooling rates also offer advantages in making high-end copper alloys, as listed in this slide. Compared with as cast dendrites, the sprayed copper alloy is a fine and uniform single-phase equiax grain with very uniform chemical composition, which effectively inhibits the segregation of elements such as SN, tin, and greatly improves its performance compared with as cast dendrites. An example of high-performance copper alloy is Pune 15 SN8. You can see heavy dendrites in as cast structures, whereas PSF alloy is fine and uniform, with best alloying efficiency. The strength can reach 1,200 megapascals. There are also some high value-added materials that we can mass produce now, which cannot be produced by traditional methods. This is a production line with capacity of 10,000 ton per year and single ingot weighing 6 tons. Fangha makes the turnkey project from design, manufacturing, installation, debugging, and running services. PSF technology has a significant industry influence worldwide. The inventor of PSF, Yang Yingfeng, was invited to attend the 75th World Foundry Congress to give the presentation and received Best Technical Paper Award. PSF technology also has great significance for a country. Former national leaders, such as Li Keqiang and Hu Chenghua, had thought highly of PSF. And the central and local governments have always provided great support for the development of this technology. At last, let's give a summary of the PSF introduction. Firstly, super rapid solidification and short process flow make PSF technology a flexible and cost-efficient in making high-performance alloys, with fine and uniform microstructure and outstanding properties. Secondly, in many high-end applications, PSF simultaneously make multiple improvement of the material or components in properties or lifetime, costs, and lead time. Finally, Fenghe has the complete IPR of PSF technology, also capabilities in material and process R&D, as well as in building up full sets of PSF production lines, aiming to serve high-performance metallic requirement in the world. On behalf of Fenghe PSF Technology Limited, thanks for your attention.